Great. So my name is Rob Emanuel. I'm the maintainer of a project called Geotrellis, and I'm here to talk to you today about distributed tile processing with Geotrellis and Spark. So first, I'm going to ask a motivating question: sort of how do we work with very large raster data? And when I say very large, I mean raster data that you'd need to work on a cluster with. It won't fit into the memory of one machine, even a beefy machine. And also, if we want to do it, process this data quickly. And usually with this talk, I'll mention a couple different data sets, but I'm going to specifically talk today about the NASA NEXT downsampled climate projections open data set. So how do we work with this data set? So what is this data set that we're talking about? There's these things called global circulation models, which are models of worldwide temperature and precipitation, and it predicts out those data points over about 100 years to try to measure, what climate change is happening. So there's an organization called the Intergovernmental Panel on Climate Change, and they publish a assessment report about every 5 years. That's a sort of a scientific curation of the outputs of these models and the data that we have available. And it's collaborated on by more than 800 authors worldwide. Some of the best minds that are working on climate change are working on this data. And we can organize the model data into 3 key categories. There's the different models that are run that come from all over the world, different scientific institutions, and then there's model ensembling, so we take averages over the models. It outputs 3 different data sets. There's a temperature max, temperature min, and precipitation. And then there's scenarios that they run over. One set is like a historical run from 1950 until 2006, and then there's these things called RCPs, which are carbon emission scenarios that basically say, okay, how is carbon going to be, how is the human race going to deal with carbon emissions over the future? For example, here's 3 of the 4 RCPs that are included in the next data set. RCP 4.5 says, all right, carbon emissions will peak in 2040, around 2040, 2050, and then go down to lower than current levels, which would be pretty awesome. And then RCP 8.5 says we're just going to continue business as usual and keep pumping carbon into the air. So the next downsampled data is monthly data over the United States. It's downsampled, so it's pretty high resolution for this type of data set. And there's 4 RPC scenarios included from 2006 to 2009. It's available on S3 publicly as over 8,000 net CDF files that are about a gig or so each. And we, as part of our pre-processing, we exported to GeoTIFF tiles, and so I measured how big that was. It's 15.3 terabytes. And even for one combination of one model, one data set, and then one RCP scenario, like a max for one of those is like 90.92 gigabytes. So even if you're working with one data set across that time period, it's pretty large. So I want to talk about our workflow for working with this data set. Some of the tools that we use. Like I said, I'm the maintainer of Geotrellis. What Geotrellis is it's a Scala library for doing basically anything geospatial. We have library functionality for doing vector processing, reprojection, GeoJSON stuff, but our main focus has been on raster processing, doing really fast and optimized single tile, just like single threaded, chunking through raster data and doing complex geospatial operations on raster data. And then it's also a framework for doing distributed raster processing over tiled rasters. We have our main framework that we've had historically is based on ACA and works really well for if you can fit like a raster in a single machine and it has a bunch of cores and it can parallelize over that tiled raster data on a single machine. But most of our current development is focused on integrating with Spark. And I'll explain what Spark is later. And we have, for people who know what map algebra terms are, we have all these local, zonal, focal, and global operations implemented on raster, and we're currently at incubation at Location Tech. So for those of you who don't know what Spark is, it's fast and it's a really fast cluster compute engine. It's could be described as like a next generation Hadoop structure. If you do sort of like larger data processing and you don't know what Spark is, then get on the ball. It's really gaining steam these days. It's written in Scala, which is nice for us because we integrate really well with it. But it also has bindings for Python and Java. And for our backend, we use a Cumulo, which is a big table implementation on top of HDFS. So we use that to store our tiles and do some indexing. Cumulo gives us really good precision about where we want to store tiles and be able to do range queries on how to get tiles out of our store. And another great point about Cumulo is that it's used by GeoMesa, another location tech project that Andrew had mentioned, which is a Scala project, and we hope to be collaborating with them in the future even more. So what are some strategies working with these big rasters? One thing is to just tile the raster. So if you have a very giant raster, you just break it up into the individual tiles and work on the individual tiles. That's one strategy. So those are spatial tiles, but you could also have spatial temporal tiles, where you would look at the tiles as sort of a stack of tiles in 3 dimensions, with third dimension being time. And then you can index these tiles, sort of project the 2-dimensional or 3-dimensional index schemes onto a single dimension using what's called a Z-curve, or geohashing in the 2D sense. On the left, we have the 2-dimensional Z-curve that allows us to index the tiles in that way, and then the harder to look at 3-dimensional Z-curve. And the Z-curves are nice because they allow us to do range queries of continuous spaces in the 3-dimensional space or 2-dimensional space, and not have to query individual tile IDs. We can actually turn them into a set of ranges in the Z space. And so Spark provides this idea called a resilient distributed data set. That's sort of the core data type in Spark. And it allows you to look at a large data set across a cluster as sort of a single collection. It lets you do functional transformations on that RDD. So what we provide to Spark is a Raster Rdd, and that a Raster RDDK, where the key type is generic and based on the tiling, so the indexing. So we support spatial only tile rasters, or rasters with a spatiotemporal key, or the easier to say spacetime key. So the first thing we have to do to get this next data set into Geotrellis is to do some data loading. So first off, NetCDF is sort of tough to work with because it's just all packed into these large files. So the first step I did was just use some Rasterio Python code to take the NetCDF format and then tile each of the bands of that raster into 512 by 512 geotiff tiles. And that's a really embarrassingly parallel problem. You can kind of just fire up some EC2 instances that read from a simple queue service that takes the NetCDF file, downloads it, chunks it out, and then throws it into another S3 bucket. So we don't really need complex indexing for that sort of step. So the code's on my GitHub if you want to take a look at that code. And the next step is to ingest the data into Cumulo using Geotrail Spark. So that process is a little more complicated because we are indexing the tiles. We actually take the geotiffs off of S3, reproject them into Web Mercator because we want to view them on a map. We mosaic the tiles into a TMS tiling scheme, so we determine what zoom level should fit to, and then take the tiles and kind of make the web tiles out of the tiles that are incoming. And then we can pyramid up the zoom levels and calculate the index splits to give to a Cumulo so that it stores them very efficiently. And what we end up with, I wrote a little catalog viewer that looks like this. You can see that I have CCSM4 is a model type, and RCP45 is the carbon emission scenario where we curb carbon emissions in the future. And we can see we have a number of zoom levels and the dates for each of the months for just 4 years. We can go ahead and take a look at that on a map. And then here's RCP85, which is carbon emissions that are actually a lot higher. And you can see that there's, the bluer is colder, so you can see that the RCP 85 is less cold. Let's take a look at, in 2060, in August, what that looks like. The RCP 45, there, in this case, the more red, the more hot it is. It looks like this, and then the RCP 85 with the higher carbon emissions, you see a lot more red. So this should be enough to convince you to curb your carbon emissions. I mean, do you want to live in this world or this world? No. All right. So now I want to do some live coding with Geotrail just to show what it sort of looks like to work with this data, not on a map, but actually in a console. Great, so this is all in Scala, so apologies if you aren't familiar with Scala, but hopefully you'll be able to follow along. First thing I'm going to do is just do some imports of some of the functionality, the raster package for Geotrellis, the vector package, and the Spark. Import a Cumulo, and I need a password token, and then make this Spark context implicitly available. So first thing we're going to do is connect to a Cumulo. And we see some Zookeeper output. Zookeeper kind of keeps track of what a Cumulo is doing. So now we're connected, and there's a catalog attached to the Cumulo instance, cumulo.catalog. And in Geotrellis, the idea of a catalog is just what you load data out of or save data into. So I can start loading data out of this by doing catalog.load. I have to strongly type the key type so that I get an RDD that's actually typed on the space-time key. And then what was that model name? CCSM4-RCP45. And let's work with zoom level 5. And oh, you know what? I need to put in the layer ID class. And that's it. Great, so we can do the same thing with RCP 85, and now we have these Raster RDDs that represent all of the tiles for that data set. And if I import some operations here, like local raster operations, I can do things like take a difference of those two rasters. So I take RCP 85 minus RCP 45. Great, so now this gives me a Raster RDD that represents the work that'll give the difference between the two rasters. It hasn't actually done anything yet because I haven't asked it for any results, but let's do something easy and take the min and the max of that raster. You'll see that Spark kicks off, and I get some results, and we see that it's -14 and 18. So this would mean that in some of the cases, the RCP 45, the lower carbon emission scenario, it has cells that are warmer than the corresponding raster that's the RCP 85. Which shouldn't be surprising just because they're different model calculations, but what would be surprising if there were more warmer cells in RCP 45 than RCP 85, right? Because we're kind of expecting the more carbon in the air, the hotter it's going to get. So that I'm currently working on my local machine is like 30 gigs, I think. What was that? One band. It's like each band, so 1 month's data over is a set of tiles. Each of the tiles are 512 by 512, but the total area of the United States, I think, is like 7,000 by 5,000 roughly. Great. So what I can do here is just do some like functional calculation on the difference to say if I take a local if operation, which takes a function that says for each value, if the value is data, we want to ignore no data values, and it's above 0, which means that the RCP 85 is actually warmer, then assign it 1, or else assign it 0, right? And I can kind of store that off temporarily. Great. Live coding. Great. And then so now I have another raster RDD where all the tiles are either transformed to 1 or 0 based off of if it's warmer or colder. So what I can do with this, I can map into the tiles, do its little tuple unpacking, and then take the tile, and all I want to do with the tile is do to array double and take the sum of it. So now this gives me a RDD of doubles that are just represent the sums of each of the tiles, and then I could just do a sum of that RDD to get the total sum, and you'll see that Spark kicks off and actually calculates all of that stuff. So we get the hotter value, the hotter cell values is that number, and then I'll just cheat and take the colder values, and we get another number. And if everything works out, then hotter minus colder should be a large number. So there are a lot more hotter cells in the RCP 85 scenario than the RCP 45 scenario.
Are you running all of this in localhost?
Yeah.
Okay.
Yeah, this is all local.
But you probably can't fit 30 gigs in your memory, right?
Yeah, so Spark does like some spillover stuff. So it just loads different partitions of the tiles, works on them, and then throws it does all the memory management for me, which is really key because I don't. that's a tough problem that they solve. I don't want to have to solve that. All right, another thing that we could do is actually save off a raster. So instead of looking at just the difference with the negative values, I'm going to look at the absolute difference between the values. So I can use a local absolute value function, which takes the absolute value of each cell, and then I could do something like catalog.save, call it, give it a new layer ID, call it diff. It's at zoom level 5. I'm going to give it the table to store the tiles in a Cumulo, and then give it abs diff. Boom. So this is actually chunking through some data. Let's see if I did this right, and you should be able to see. Yeah, see, this is the Spark UI, and you see it actually saving off the value. And so this is the 36.1 gigabytes is like how big the RDD is. And then right now it's also calculating a histogram for the whole entire raster because the histograms are really useful for visualizing. So it just calculates the histogram and saves that off into metadata. And so now if I restart my service, boom, we should be picking up that new layer and be able to look at it, which we can. Awesome. All right, so I colored this a little differently just because this is easier. The lighter green is lower values and the higher green is larger differences. And you can see I didn't do any pyramiding to this raster layer, so it's only at zoom level 5. So if I try to zoom out, it'll pop off. Great. How much time do I have left? About, what's that? 5 minutes? Okay, great. Let's try to go through this part of it. So I might want to do something a little more complicated. Say I want to find the tile in the difference, the absolute difference that has the most variance, so the greatest total difference. For that, I'm going to do sort of the sum calculation again, but I'm going to do something a little different. I'm going to map over the tile and tile ID and tile again, take the sum, but keep the tile ID and tile sum data because I'm going to actually look at that later. Oops. So let me just paste that in instead of typing all that out. Great. And then what I could do now is that's called diff sums. And then I can do the Spark RDD max operation, but I need to give it an ordering because it doesn't know how to order this tuple type. So I could do the tuple unpacking again. So this is the ID. We have the tile and the sum. And then I'm going to say just order it by the sum. And sweet, thank you. Yep. Boom. And then so this is this should be the tile ID, or like let's call it key, the tile, and the sum. So Spark kicks off, does the max operation. It does the map and the max operation. So I get the sum and I get the tile. Oops. Tile, and I get the key. So if we look at that, the key says it's 2058-03, so March of 2058. We can go ahead and take a look at that. 2058-03, boom. And you can see that here's a pretty large difference. So I can kind of guess where the tile would be, but instead of that, I'm going to actually put it on the map. And this will show some vector capabilities of Geotrellis. First of all, I'm going to import some stuff to work with vectors. Sorry. Great. So I'm importing the reprojection logic, the GeoJSON logic, and then also proj4 so I can specifically name these the CRSs. I have a utility function. Just write JSON to a file that'll paint it on the map if it's there. So so I want to find the extent of that key. And if we look at the key, it gives me the datetime, but it also gives me this like tile coordinate for the key. So we have some metadata that can allow you to turn that into a map extent. And that'll be in Web Mercator, so I'll call it Web Mercator extent. And then so what do we diff.metadata .map transform the key. So we should get a Web Mercator extent, but I actually want the it in lat long, so I do wm extent dot reproject from Web Mercator to lat long. Great. So now I can just write that JSON out, just turn it to a polygon, and then to GeoJSON. And now that should actually show up on my map if I did all the things correctly. Yep. So now we get the extent of the tile in lat long that we can put through a web service and just paint on a leaflet map. I think that's all the code I wanted to show you. There's some more stuff about calculating isochrones, but I don't really have time for that. So, thanks. Live coding. Whew. So I'm going to hand it off to my colleague Johan. He's going to talk about the reader that we use to read those geotiffs that we put into S3 from the netcf files.